All right. This laboratory exercise is a qualitative exercise, and it's going to involve equilibrium. When we say equilibrium, we're talking about a chemical reaction of sorts that has some components on one side, and they yield some products on the other side, and you reach a point in this reaction where the reverse reaction is equal to the rate of the forward reaction. At that point, the reaction is said to be in equilibrium. What that means is the products are forming fast enough. The reverse reaction, where the reactants are reforming from the products, is happening fast enough to replace them as fast as they can go in the forward direction. Now, a whole host of different types of reactions can fit this scenario. So today, our equilibrium types are going to be broken into three different types. One is solubility. The other is complex ion. And the third is acid-base. Okay? That might look really difficult, but believe me, it's not. Solubility involves some solid that we're trying to put in solution. So let's say we have, our first example is going to be sodium chloride. Right? So when sodium chloride goes into solution, it produces sodium ions and chloride ions. And we start with a solid. Right? So the medium is water. Right? So the equilibrium is between the dissolution of sodium chloride into its aqueous form, the individual ions, and then the return, precipitation of these into sodium chloride. Complex ions. This is a little more involved. A complex ion is simply the association, usually of a metal, with some group, in this case ammonia, and it forms a stable complex in solution. So we get an association, in this case, of silver ions plus ammonia. Takes two of them actually. And we form this silver di-ammonia complex. And it's still soluble. All right? So in this case, the reaction is occurring in solution, both sides. Now, what we're also going to do with this is to couple a reaction with another reaction. And I'll have to describe that as we go. Acid-base reactions are, well, the net reaction is the proton from the acid plus the hydroxyl from the base yields water. That's the net ionic equation for all acid-base reactions. And we're also going to couple this one with other types. So, why are we studying these reactions? What we want to see is the effect of a disturbance in the equilibrium. So if we've established an equilibrium here in any one of these situations, we're going to do something to it that disturbs the equilibrium. One possibility is we could add chloride ions to the solution. What's going to happen? Well, if we add extra chloride ions in an equilibrium situation, the reaction is going to be driven back this way. Some of these are going to be consumed and pick up some sodium ions from solution and make solid sodium chloride. So you should see a precipitate form. Okay, that's one type of perturbation. LeChatelier's principle, simply stated, is any system in equilibrium, when it is stressed, will react in a way to relieve that stress. So we stress this system with chloride, and to relieve it, it used some of the chloride to reverse that reaction. Okay, that's LeChatelier's principle in its simplest form. Now, that's an introductory statement, and let's get to the procedure. Okay, I've set everything up here, hopefully in logical order, so that we have everything we need to conduct the experiment, and it's going to be a series of individual exercises. So we have to pay close attention to what's happening, and the procedure I've got here, and I've got my key here to show me where this information goes. And the procedure numbering system is correlated with the same numbering system in the results and observations, beginning on page 7. Okay, so yours is going to look like this. There's your front page, and we've been discussing this so far. Now we've come to the procedure. All right, so the solubility equilibrium. Let me put on some gloves, because I'm going to need them eventually. Safety precautions. We should mention a word about that. Safety precautions. Things like sodium chloride, any of these dilute types of solutions like iron 3 chloride, the solid ammonium chloride. Silver nitrate is not particularly hazardous, but we do have some concentrated solutions. 1 molar sodium hydroxide is caustic. 1 molar hydrochloric acid is caustic. We also have concentrated hydrochloric, approximately 12 molar. Okay? So this one is very dangerous. We'll do this part of the experiment. We may not have to do it under the hood, but I might. Let's just see what happens. But be careful with that one. Also, there is concentrated ammonia solution. It's identified as ammonium hydroxide, but the dominant form of ammonium is ammonia, NH3. And this one is 6 molar nitric acid. It's very dangerous too. So notice the dangerous ones we have in secondary containment. In case anything happens to the vessel, we have something to catch it. So if that one breaks or if this one springs a leak, we have a secondary containment to hold the vessel, hold the solution. Okay, so let's get started. Solubility equilibrium. This is step number 1A. So the procedure says that we need 5 milliliters of saturated sodium chloride solution in each of 2 test tubes. So here we have 2 test tubes, and we need 5 milliliters of sodium chloride in each. Let's see if I can do this freehand. This is a 10 milliliter graduated cylinder, and this is not a hazardous material, so I'm going to try 5 milliliters. Here we go. Put it in this one. And 5 milliliters in the second one. There we go. This is procedure 1A. All right, now let's clean that out in case we have to use it again. We don't want to contaminate our next experiment. And we'll lay it down like this so it'll drain. Okay. Now that we have those two, what are we going to do with them? Well, the system is, as drawn on the board, sodium chloride solid is in equilibrium with sodium ions and chloride ions in solution. Right? So let me stop and make a point here. When you're describing what happens to a solution, to an equilibrium situation, if you say that we disturbed it by doing something and then the equilibrium shifted to the right, what does that mean? It only means something intelligible if you have an equilibrium expression written like this. Then we can say it moves to the right. But if you say it moves to the right and you don't give your readers an equilibrium equation, then they don't know which way you mean. Because if you write it wrong, if you write it back this way, then to the right says you're forming more solid. If it moves to the left this way, you're forming more solid. But if you write it backwards, then to the left means you're forming more ions. So when you say moves left or moves right, you have to reference an equilibrium equation. So keep that in mind when you answer questions. When you answer questions, write an equilibrium expression. Then you can say right or left, formation of this ion or that ion, or this solid or this complex ion. It makes sense then when you have an equilibrium equation that's central to your discussion. All right, so let's get back. We've got 5 milliliters of sodium chloride, and this is a saturated solution of sodium chloride in water, which means that the solution can hold no more sodium chloride. In other words, if we put sodium chloride crystals in here, they would just sit, and they would appear to do nothing. Now, of course, they're not just sitting there. Microscopically, there's an equilibrium exchange going on, but the amount of sodium chloride would not change. That's saturated solution. So now that we're saturated, we have this equilibrium as described on the chalkboard. And what are we going to do next? We're going to add 10 drops of 12 molar HCl to one of the test tubes. 12 molar HCl. Here it is, concentrated HCl. And if we're careful, we can do this on the bench. So we need my dropper. There, the cap's loose. Now, what do you think is going to happen if we add concentrated hydrochloric acid? What are we adding? We're adding protons. We're adding chloride ions. Now look at your equilibrium expression. If you're adding protons, are there any protons in that expression? We're looking for what we call common ions. There are no protons in that expression of sodium chloride dissolving in water. So the protons have no effect. It is not a disturbance. But the chloride ions we add, yes, we are changing the concentration of chloride, changing the concentration of chloride in that solution. So which way is the equilibrium going to shift? It's going to shift to the left as we've written it and form sodium chloride solid. So we should see a precipitation. Let's see if that happens. 10 drops of concentrated hydrochloric acid. Notice it's fuming, so you don't want to breathe any of that stuff. So let's say, okay, 1. Look what happened. Let me hold it against a dark background. You see that? We're forming sodium chloride from a saturated solution. We don't even have to add the rest of it. All right. So your description then is you observed the formation of sodium chloride crystals upon addition of concentrated hydrochloric acid. And the explanation is that the disturbance to the equilibrium was addition of chloride ions to increase chloride ion concentration. It's all based on concentration. So when you do that, you're adding a lot of chloride ions, but very little water. Now the next step is 10 drops of 1 molar hydrochloric acid. So let's get another dropper and do the same thing to the second tube and see if anything happens. Five. 1, 2, 3, 4, 5. 10 drops. Has anything happened? No. The solution is still clear. So, what does that mean? That means that we did not disturb the equilibrium. Why? We added chloride ions. We also added a lot of water. And equilibriums are always based upon concentrations. So if we add a lot of water along with the chloride, then we effectively do not change the chloride ion concentration. And we will not get a precipitate. Okay? So that's 1A of LeChatelier's principle. All right. So let's set that one aside so we don't reuse it. We'll leave this one with the concentrated hydrochloric in case we need it again. Yeah, let's see. On the side here. Just so we don't get them mixed up with the other dropper. Okay, the second one. Saturated iron 3 hydroxide solution. We have to make this solution first. So in order to do that, and iron 3 hydroxide is insoluble. We say it's insoluble, but it's slightly soluble. So some of it is in solution. And the descriptive reaction, and you can read this right here on the page, is FeOH3, solid, is in equilibrium with iron 3 plus ions in solution and OH minus ions in solution. Okay, so we have to make that solution first. So we need 2 milliliters of 0.1 molar iron 3 chloride. We're going to do that in a separate test tube. 2 milliliters of, actually, I know these droppers will contain about 1 milliliter when full to the bulb. So if we do 2 full bulbs of iron 3 chloride and 2 full bulbs of 1 molar sodium hydroxide. Here's 1 molar sodium hydroxide, and here's 0.1 molar iron 3 chloride. So let's do 2 dropperfuls. This is 2 milliliters. Oh, not enough. A little more. That's close enough. So 1 drop of that. And there's a second one. That's iron 3 chloride. And then another dropper for the sodium hydroxide. Okay. Let's see what happens when we make the solution. Whoa. See that? What we have formed is iron 3 hydroxide. And I'll shake it up on the walls of the tube and you can see there's a solid in there. That's iron 3 hydroxide. Let's see, I think we need 1 more. Okay. Now, we've established an equilibrium situation where we have iron 3 hydroxide solid in equilibrium with solution of iron 3 plus ions and hydroxyl ions. Now we're going to disturb the system. Add 1 molar hydrochloric acid to the system, 1 drop at a time, until you see a change. Now, what's unusual about this is that, remember I mentioned common ions. If we add hydrogen and chloride to this solution and this equilibrium, we're not adding a common ion to that equation. Now, of course, we formed from chloride, so we're adding chloride. But the equilibrium we're discussing is iron 3 hydroxide in equilibrium with its dissolved components. So if we add 1 molar hydrochloric acid, drop-wise, let's see, I think this was the one we used. Yes, that's the one we used before. And we're going to look for a change. All right, so here we go. Are we supposed to mix as we go? Not necessarily. Let's see what happens if we don't mix. It looks to me like we're getting some clearing up here toward the top. Now, we haven't mixed it yet. So let's see if that clearing progresses as we add more hydrochloric acid. Yes, it's going further down. So what's happening here? We're disturbing the equilibrium because there is a change. So let's add a little more before we mix, and then we'll mix it and see what happens. Okay. Well, that wasn't very smart. Fortunately, 1 molar hydrochloric acid is not very hazardous. Now hold it firmly at the top and mix. Okay, what's happening? We're getting clarification. The solid is disappearing. It's still dark. All right, it's still dark. There we go. So what we see is that the dark brown precipitate has disappeared. We still get what we're getting is a clearing, but it's still got a color. Right? So the solid dark brown precipitate did disappear. So what has happened? If you look at your paper, And don't spill things on it like I did. Look at your paper at the reaction. So what's happening? Well, we're adding hydrogen ions first. So what are the hydrogen ions doing? The hydrogen ions are combining with the hydroxyl ions to make water. So what does that do to the reaction? As written, it moves the reaction to the right toward the formation of Fe3 plus ions and more hydroxyls. So where does it get those? It consumes them from the iron hydroxide solid, which means that solid has to disappear. And we also are adding chloride ions, which actually don't matter. They're spectators. The important part of the reaction is, let me write that on the board. I think it'll make more sense if I write it here. So here we have, this is the equilibrium that we established. There's your precipitate. And it's in equilibrium with these ions in solution. Okay? We saw a whole bunch of this dark brown precipitate. Now, we added hydrochloric acid, which means we added protons and we added chloride ions to that solution. So, what does it do? Well, the chloride and the Fe3 plus, they're both completely soluble. So they're what we call spectators. But this proton and that hydroxyl combine to form water. And the reaction is very strong to produce this and very little of that. So it drives the reaction this way, and these two reactions are coupled. We're coupling this reaction with that reaction, and in the process, we're removing hydroxyls from this equilibrium. The disturbance is the removal of hydroxyls by reaction with, according to LeChatelier, says it's going to make more hydroxyls. And the only place it can get those hydroxyls is from here. So the reaction shifts that way. All right? That's what's happening in 1B. Okay. That's it for solubilities. Now we're going to go to complex ion equilibria procedure number 2A. So let's put these back out of the way before I tip them over again. Here we go. Now, I don't remember where these came from, so they get set aside. Next thing we need to do, we need to prepare a stock solution of the complex ion of iron thiocyanate. And we do that by mixing 0.1 molar iron 3 chloride, here, and the thiocyanate ion, which is contained in this solution. Okay? So the thiocyanate ion, this part of that molecule, combines with the iron in this one and forms a complex ion. And it's right there in your procedure, written out for you. So first we're going to prepare the stock solution and discover that it's very densely colored. So we have to dilute it so we can see what's going on. So we need 2 milliliters of iron 3 chloride and 2 milliliters of potassium thiocyanate solution. So set that over here so we don't get it mixed up. And we're going to, and one of the videos I did, chemical reactions, identifying chemical reactions, I cleaned up all these tubes. So I know those tubes are clean. So 2 milliliters of iron 3 chloride. There's 1. And there's 2. Now we need, oh, this one's got a cap on it. That's not a problem. I just need a, pop the cap off. And there's 1. I want you to see this when it happens. So there you go. There's a solution, iron 3 chloride only. Now we're going to add the thiocyanate ion. Oh, there you go. That complex ion with the iron and the thiocyanate together forms this brick red color. But I need 1 more ml to complete the stock solution. There we go. Now, notice, of course, that's way too dark. We couldn't see a change in there to save our lives. So we need to dilute it. Okay? So to dilute it, that solution, we're going to take that entire 4 milliliters and dilute it with 100 milliliters of water. So we need 100 milliliters of water. Approximately. There we go. And this is a clean beaker that I rinsed out earlier. So let's transfer the stock solution in here. There we go. And dilute it with 100 milliliters of water. There we go. Still pretty dark, isn't it? All right, let's stir it around a little bit. Mix it up. There we go. That had water in it. We can leave that to drain. Rinse that off. Now, what do we do with it? Now, we're going to take 5 milliliters each for 4 separate test tubes. All right, so we have 4 tubes. We're going to label them 1 through 4. Let's see. That one is a 1. This one is a 2. Here we go. This one is a 3. With my grease pencil. And this one is our 4. And we need 5 milliliters of each. All right. 1 milliliter at a time is too slow, so I'm going to use a small graduated cylinder for this one. 5 milliliters. I put my fingernail on the 5 so I don't have to look at the number. I just know where my fingernail is. There you go. So here's 5. Up to my fingernail. Here we go. There's 1. Okay. My fingernail set again. There we go. And this goes up to right there. Put that one in number 2. Set my fingernail again. Fill to the nail. Here we go. 3. And number 4. Went a little past, but this is qualitative chemistry. We only have to be approximate. All right, let's set that solution aside. We'll dispose of it later. And rinse out our graduated cylinder. Okay. Now, what are we going to do with each one of these? Get those drops down in there. Set this back over here. Side. Now, we have those 4 tubes. Number 1 will not be disturbed in the least. It's our comparison tube, so we can see if there's been any change in color for the others. Test tube number 2. We're going to add dropwise with a medicine dropper about 1 milliliter of iron 3 chloride, 0.1 molar iron 3 chloride, and see what happens. So here's iron 3 chloride, and I can't remember which one of these is which, so we'll set it aside. Better safe. So 1 milliliter. That's good enough. And let's not spill that. All right. So this is test tube number 2. Add dropwise and see what happens. Well, you know what? I think it's getting darker. Let's finish putting it in there. And compare it to our other one. Oh yeah. Huh? You can actually get some light coming through this one. The control, we call it. This one is completely blacked out. So we have formed more of the iron thiocyanate complex. So how does that work? Well, let's look at the equilibrium equation that operates in this case. Okay? So we have iron 3 plus, and this is aqueous, plus thiocyanate ion aqueous in equilibrium with the complex ion FeNCS. So what do we do? We just turn this thing around so it's facing the iron. But it still has a charge. It has a 2 plus charge. Why does it have a 2 plus charge? Because when you add 3 pluses to 1 minus, you only have 2 pluses left. Okay, and this is in aqueous solution as well. But this is that brick red. All right? So what have we done? Well, we had a diluted solution where we could actually see some light through the solution with the iron thiocyanate ion, and it was in equilibrium with some iron and thiocyanate in solution. So what we did was add FeCl3, which supplied 3 plus iron ions. We added those in here. There's your disturbance. So how does the system respond? It consumes some of these and makes more of that. That's why the solution got darker red. Okay, that was tube number 2. How about tube number 3? Tube number 3. Add dropwise with a medicine dropper 1 molar 0.1 molar potassium thiocyanate. So we need potassium thiocyanate, and we're going to need another dropper. And we're going to add how much? Milliliter. There we go. So this is tube number 3. Right, there it is. Let's hold them up there together. Right, they're the same color. Right, you can see that. Same color. So we're going to add to the number 3 tube. And let's see what happened. Let's hold it against a light background. Now, it got darker red, but it didn't get quite as darker red as the one where we added iron. So, we get the same shift in equilibrium that we did before, only this time the disturbance was adding thiocyanate ion. Right? I'm not going to go over to the board for this one because you've got sense enough to know that instead of adding iron this time, we add thiocyanate, and we get the same result, that we observed a darker red color by the formation of iron thiocyanate complex ion. Okay, now what are we going to do? We've got one more tube, and the procedure says tube number 4, you add silver nitrate solution dropwise until a change becomes evident. Silver nitrate, here we are, dropwise. So it doesn't say how much, it just says add until you see a change. Okay, I'm guessing that we're not even going to need our control to see something happen here. Okay, let's do this. Can you see that? Tilt my head down just a little bit. So what's happening? Looks like we're losing the red color. Oh yeah. And we're gaining a lighter colored precipitate because it's not clearing up. It looks like we're curdling milk. Right? Can you see that? Hold it against something dark. All right. So what we formed, there we go, you can see it swirling. What we formed was a precipitate. So we added iron nitrate. Silver nitrate. We added silver nitrate. I'm going to have to show you this one on the board. Okay. So, yes. Okay. So here we have a coupled reaction. We're still looking at this equilibrium. And we've got that brick red color. But we added silver nitrate. Silver nitrate is soluble in water. It forms silver ion and nitrate ion. Let's take the nitrate first. What does nitrate do? Well, all nitrates are soluble. Look it up. So nitrate with this iron is not going to form a precipitate. It's not going to even form a complex ion. Anions don't react with one another, so that's out. Nitrate does not react with this one because it's stable the way it is. So The only candidate we have left is silver, so silver must be doing something. All right? So we have a coupled reaction, which means that something from this one has to react with something from that one. And what it does is silver reacts with thiocyanate. That's the disturbance. And it produces silver thiocyanate solid. And this is that white, curdled-looking material. Right? So in the process, where does it get that? Well, it uses up what it's got on this side, but there's a lot of it. So the disturbance to the system removes this ion, and in order to replace it, the shift has to be back this direction, to the left. Okay? So when it does that, these two form that white solution, and that brick red color disappears. All right? I can't put it any simpler than that. Now, that was number 2A. So we're finished with 2A. Now we're moving to 2B. We're going to use silver chloride again. Let me set these over, move them over just a little bit. Okay. We're going to set up the equilibrium, and that's been the pattern. Each time we have an equilibrium established or we have to create one. And in this case, we're going to, under a fume hood, it says add 2 drops of concentrated hydrochloric acid to a test tube containing silver nitrate. Okay? So we need how much silver nitrate? 10 drops of silver nitrate. Okay. Silver nitrate. Here we go. So our test tube needs 10 drops of silver nitrate. Let's use a smaller tube. Let's use this one. Right. So we're going to put 10 drops in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Silver nitrate. And then we need concentrated hydrochloric acid. And we're going to go to the fume hood to do this one. You know what? We should be under the fume hood, but I'm going to be really careful. And the reason I'm doing it out here and not on the fume hood is because with the fume hood running, you can't hear me. And my voice is essential to conducting this experiment. So don't do this at home, kids. Don't even do this in the lab. If you were here doing this yourself, you would do it under the fume hood. But I'm going to do it freehand on the bench top. And be very careful and keep my breathing distance away from it because concentrated hydrochloric acid is fuming. You might even be able to see some of the fumes. Okay, now we're going to add 2 drops of concentrated hydrochloric acid and see what happens. One, 2. Wow, that was instantaneous. We formed a precipitate. How do we know? You can't see through it. And it's not because of the color, it's because of the clumpy solid in there. Okay, now we have established an equilibrium. We added chloride ions to silver ions. All right, so let's put that on the board just for a second to show the equilibrium that was established when we added hydrochloric acid to silver nitrate. And notice we use concentrated hydrochloric acid because we don't want to dilute anything. We want a concentrated amount of chloride to interact with silver ions. And remember, the nitrate, all nitrates are soluble. That's how we got silver ions in solution. That's the only thing we care about. The silver nitrate produces silver ions in solution, and we're acting with chloride ions from the hydrochloric acid, and we are forming an equilibrium with the solid. Now let's see, is that the way they write it? Because normally this would be a solubility problem, right? So in order to be a solubility problem, we would write it this way. Okay? See, it does depend on which way you write it as to how you discuss it. So let's use the solubility version of this equation. In equilibrium, right? So we've got silver ions, chloride ions, a very small number of them in solution, and mostly this white precipitate. Okay? That's what we've established as our equilibrium. Now what are we going to do next? The next thing we're going to do is we're going to allow the solution to settle, and it's been settling for maybe, well, almost 5 minutes actually. That's what the instructions say. Settle for 5 minutes, and then under the fume hood, add concentrated ammonia solution, dropwise, until you see a change. Okay? So we have set this one over here with its dropper. And then we need ammonia, which is here. All right, so it doesn't say, does it say how much? Concentrated ammonia, just dropwise. Okay. Concentrated ammonia, this is 15 molar, which is very concentrated. The solution you get in your off-the-shelf ammonia solution at the grocer's to clean things around the house is only about 1 or 2 molar. It's very dilute. But it still stinks. Okay, so now we're going to add some of this and see what happens. Dropwise. And nothing major yet. Another drop. Okay. So what's happening? It appears to be clarifying, that is, consuming the silver chloride. Let's add some more and see if we can drive the reaction completely. Yeah, it's getting there. Okay, see, it's starting to clear up. There's still some solids in there. So silver chloride is still there, but if we keep adding, I'm thinking that the more we add, the more silver chloride will be consumed in a coupled reaction. Yep, we have some pretty big clumps in there, and what that does is it excludes ammonia from attacking the interior of the clump. So that slows down the reaction. Let's add more. You see that? You still see some clumps in there, but we've clarified everything that was finally divided. And in the interest of time, I'm going to describe for you what actually happened. On the board. So let's go over to the board and see what happened. Our equilibrium was silver chloride solid and in equilibrium with silver and chloride ions in solution. So what did we do to disturb this solution? Well, look at it this way. The solid was partially consumed. It disappeared. So it had to move with this expression to the right because something was being withdrawn from this side to drive the reaction that way. So which part of it is being withdrawn? Well, if you add ammonia, ammonium and chloride, because here's what you have. You have mostly this, and let's see, water. OH. So most of it is over here. I've done the calculations, and I can show you that. I've got the document. I've done the calculations, and the equilibrium is way over here. 98% ammonia molecules. So when we add that solution, which may be labeled this, but it's really that, we're adding this to the solution. So how can it interact with these? Well, ammonia doesn't interact with chloride because it's not an ion. Ammonium doesn't interact with chloride either because they're both soluble. They're spectators. There's no discernible reaction between this one and that one that would withdraw this one from that side. It's still there. So the only option we have is a reaction with this one and that species. So I showed you that one earlier. In fact, it's over here. The silver ions interact with the ammonia, two ammonias, to produce the complex ion, and this is very stable. The equilibrium for this reaction is way over here. Okay? So that means we're withdrawing silver ions from this equilibrium expression, and that disturbance is compensated for by moving to the right and producing more of these. All right? Simply because of the addition of ammonia. Right? So it withdraws silver ions from that other reaction. It's a coupled reaction. And that's why the solid disappears. Now let's look at it again. Now there's still some down there. So we didn't add enough ammonia to use up all of the silver chloride. We just cleared up some of it. Okay, there we go. Now, there's one other step. We're going to take this right here, and we're going to do something else to it. We're going to add 6 molar nitric acid until we see a change. So if we have 6 molar nitric acid, which is right here, and it's actually got a built-in dropper. So what are we adding with nitric acid? Well, we're adding nitrate, right? But we've already added that. So the nitrate is a spectator. That's how we formed the silver chloride in the first place. We added nitrate. So the nitrate is not going to have any influence on this reaction. Let's focus on the protons that are added with nitric acid. All right? So let me get that thing out of the way. And we're going to add dropwise and see what happens. Oh, I see something. Oh, disappeared. We had something started. We formed a precipitate, which in this environment has to be silver chloride. There's some more. All right, let's shake it up and see what happens. Okay. There we go. So we have re-prepared silver chloride. How did we do it? All right. So we added nitric acid. The nitrate has no influence on the reaction. It's just a spectator. So that means the protons are doing something. So the competing reaction that was coupled to this one was this one. Right? So if we add hydrogen ions to this solution, what's going to happen? Well, what happens is the hydrogen ions react with the ammonia that is in solution, right? See, here we've got some ammonia, and if we add hydrogen ions to this, we get more ammonium. And ammonium, NH4 plus, does not form a complex ion with silver. It's the ammonia, NH3, that does it. So when we add hydrogen ions, we are removing ammonia from this equilibrium right here. So this is a compound competing reaction, or coupled reactions. All right, let me say that again. We added hydrogen ions with nitric acid, which converted this into ammonium, which removed this from that equilibrium, which consumed this one and released silver ions into solution again. So now that silver ions are free floating in the solution because we've consumed the ammonia, then the silver ions are now free to interact with any chloride that happens to still be there in solution, and the reverse produces also. Now we've disturbed this equilibrium by adding silver ions as a consequence of that disturbance, which now reacts with chloride and produces silver chloride. And that's what the white color, the white precipitate represents, silver chloride. Okay, so that's the second step. We've done solubility, we've done complex ions. Now we're going to look at acid-base equilibrium. Okay, for this one, we're going to add 4 drops of concentrated ammonia to 100 milliliters of water. Okay, so we need a beaker that will handle 100 milliliters, and I'm short one beaker. Let me see if I can find one real quick. Let's see, this is a good one, but I don't know if it's clean, so I better rinse it out just to be safe, because these acid-base reactions are very sensitive to contaminants. So we'll just be diligent, rinse out anything that could interact with our acid bases as we perform this, as we set up our reaction. Okay. So, again, we're going to need 4 drops of concentrated ammonia in 100 milliliters of water. So here we need 100 milliliters of water, roughly. Doesn't have to be exact. I don't know if you can see that. I'm holding it so close to myself. I need to be out here where it's in the field of view. So 100 milliliters of water. There we go. And we're going to take our concentrated ammonia here and add 4 drops. 1, 2, 3, 4. That's all it takes. What have we done? We've taken a neutral solution, which is distilled water, and made it basic by adding ammonia. So by adding ammonia, that reaction on the board over there that I've already written, and let's just walk over there and say a couple of words about it. So in that solution, I added ammonia, concentrated ammonia, to water, and by diluting it in excess, we produced a small amount, but significant enough, right, to make hydroxyls. And that's where the solution now becomes basic, pH greater than 7. If I didn't know that somebody had just put ammonia in water and called it basic, I couldn't tell, right? Nothing happened. So how do we tell that the solution is basic? We use a color indicator, and we're going to use phenolphthalein as an indicator. 3 drops, and watch what happens. We get that pretty pinkish orange, pinkish purple color. Mix it up. Let's just leave that in there. We might have to mix it some more. So that this indicator in basic solution turns pink. Okay? In acidic solution, it's colorless. So that's what you're looking for, the color change between acid and base. Now we've established this basic solution. We're going to put 5 milliliters each in each of 3 test tubes. So let's move these to the back. And we need 3 clean test tubes that I know are clean because I cleaned them myself just last week. All right. Now we need 5 milliliters each of this solution. I guess I will pull that stir rod out of there. And we'll measure 5 milliliters each into these test tubes. So I need my fingernail again. There's one. And set my fingernail. There it is. There's, oops, too much. Not enough. I keep going over. There we go, right on the money. 5 milliliters. And one more. Now, if I wanted to be exact, if I wanted to get closer, I would have to hold this up at eye level, right, so I could see across those lines. But since we're only approximate, my fingernail is close enough. All right, so there's our basic solution. We're going to clean out the graduated cylinder. Let's be thorough. There we go. Lay it on its side for it to drain. Now we've got these 3 tubes with our basic solution in them. To one of the test tubes, add several crystals of ammonium chloride, which adds ammonium ion to the mixture. And we're going to dissolve it with our stirring rod and see what happens to the color. So where's my stirring rod? Here we go. Move this out of the way. Ammonium chloride, that's a solid, right? So we need a few grains of this, and I'm going to use a micro spatula so I have better control. And let's read it again. Several small crystals. All right. That's too much. Let's see if I can do this. Let's go to the edge like this. There we go. That'll do good. So the first one, we're going to add these crystals. There we go. Now, let's see, let's stir it around. Whoa! What has happened there? We lost our color. So what does that mean? That means the solution changed from basic to acidic. How can that be? We didn't add any acid. How do you make a solution acidic? By just adding the salt. Well, here's what happened. The chloride is a spectator ion. Our focus is on the ammonium. Let's see. Let's get some of the clutter off of the board. There we go. Let's get all of this clutter gone. So we have a basic pH because we added ammonia to water and produced that. Okay, now what happens when you add ammonium chloride? Well, ammonium chloride, solid, in solution, produces ammonium ions, of course, and chloride ions. So, we've added a whole bunch of these ammonium ions because this species is completely soluble. Everything went into solution. So we made a lot of ammonium. So what happens here? Well, this species right here dissociates in solution into ammonium and hydroxyls, right? Both aqueous. All right? So actually the equilibrium here is between this one and that one. So what have we done to disturb that equilibrium? We've added a whole bunch of these right here. So if we add a whole bunch of these, in order to move back to here and here, it consumes hydroxyls. So ammonium combines with hydroxyls to enter this reaction, which in turn moves back to ammonia. And what we've done is consumed all of these hydroxyls. In fact, we've consumed more hydroxyls than are available as ammonium hydroxide. We've consumed so many hydroxyls that now we're involved. We've used up all of those hydroxyls. Now we've used up all of these hydroxyls, right? And when you use up all of these, what's left? Protons. And that means acid solution. All right? So that explains that. Now we've got two more tubes. What are we going to do with them? We're coming down the home stretch. The second test tube, we add a few drops of 12 molar HCl. All right, 12 molar HCl, here we go. Concentrated HCl. And here's the pipette that I've been saving. A few drops. Here we go. 1, 2, 3. That's enough. All right. Now that one is a little more obvious. You add hydrogen chloride, hydrochloric acid, to a base, and eventually what happens is You've got your basic solution where you have an excess of these hydroxyls. You add hydrochloric acid, and what you do is consume all of those hydroxyls and add excess hydrogens. So this one is very simple. The equilibrium here is with the water. Now, those hydroxyls, of course, the excess hydroxyls, were in there from this reaction, but we consumed them with this reaction with hydrogen ions to make water. So we consumed all of those hydroxyls, plus we added excess protons, which made the solution acidic and the color disappeared. The third tube, 1 drop of concentrated ammonia. What happens to the color? And also, I've made myself a note. There's no place in the assessment. I think I must have cut off a page. There's no place in the assessment to write what happens in the third tube. 1 drop of concentrated ammonia, what happens? Add a line below it. Okay, just add an observation of the effect and explain what happens below that. And if you do that, I'll count it, let's see, 2 plus 2 is 4 points extra credit. Okay, ammonia. Here we go. So let's add, how much? 1 drop of concentrated ammonia. All right, 1 drop of concentrated ammonia. What happened? Nothing happened. Does that surprise you? What happens to the solution? It shouldn't. It's already basic, so we add more ammonia, which makes more hydroxyls, which keeps it more basic. So if our visual acuity were better, we might even see more pink color. But as it is, it's still basic. So that's really very simple. Okay, so that's the experiment in its entirety. And there are some pre-lab questions. And then, of course, your results and observations. You've been writing those down as we proceeded through the procedure. Now you have some final questions, 4 final questions after. So let's look at the pre-lab questions and see if I can give you some hints. Maybe I won't explain everything to you, but you deserve a few hints. Okay, let's get this mess off of here. And let's look at the pre-lab questions. All right, pre-lab question number 1. What do we mean by a stress applied to an equilibrium system? I told you that at the very beginning, right? That's LeChatelier's principle. What does a stress mean? Give some examples of stresses. So what could happen? How could we stress a system? It depends on the system. The system that we've been using today, the stresses have been largely changes in concentration. Okay? Changes in concentration. But there are other types of stresses that can be applied depending on the, let's see. Depending on the system. If you have gases involved in an equilibrium, and that sounds funny, but if you change the volume of the gas, there may be a gaseous reaction going on inside that container. Let's see if I can think of an example. let's see. I'm going to work from the product. N2O5 is gas. So how do we get to that one? From, let's see. No, that's not a good one. I got a better one. I'm going to have to make something up. Let's say N2O and plus oxygen no, I'm falling short. Let's say we have okay, here's one. We have hydrogen gas and oxygen gas in equilibrium with water vapor, right? So the temperature has to be pretty high. So let's balance this one. Let's say we have 2 here and 2 here. There we go. So now what happens if you change the volume? All of this is together, and they're all gases, right? So if you change the volume, let's say we decrease the volume, right? We squeeze the gases. What are they going to do? Well, the pressure is going to increase as you decrease the volume. So in order to respond and mitigate that increasing pressure, the system wants to make fewer moles of gas, because fewer moles of gas at a higher pressure don't bounce off one another as much. In other words, the smaller number of moles of gas take up less room. And if you're going to decrease the volume, you have less room. So which way would that one move? If we decrease the volume, we've got 3 moles over here, right? 1 plus 2 is 3. Over here we only have 2. So if you decrease the volume, equilibrium is going to go to the right. Let's see, what else could we do? Change the temperature. When does changing the temperature matter? If you have a reaction, and I'm going to be general in this one, if you have like A plus B is in equilibrium with C plus D, right? And you change the temperature, there's no way to tell, right? Because we don't know what the temperature influence is on that reaction. But if you are told that the reaction is exothermic, it gives off heat, then heat becomes a product. Now, with heat as a product, if we increase the temperature, that means we're adding a reactant, product, excuse me. We're adding a product, and the reaction goes back this way. Whereas if we decrease the temperature, then we are removing heat from this side, and the reaction goes to the right. That's for exothermic. For endothermic, it's just the opposite. For endothermic, heat is a reactant. And as a reactant, if you add heat as temperature increase, then you add a reactant, and the reaction goes to the right. And if you take away left, all right? So that's the first one. Oop, I shouldn't have erased pre-lab. Let's see. For the reaction as written, 2SO2 plus O2 yields 2SO3 gas. Okay. I'm not going to tell you this one. You can figure that one out. Just figure out, with that system in equilibrium, if you add or subtract any of these components, or you change the pressure, I just described what happens, then you should be able to answer 2 on your own. How about 3? Explain why the solubility of a sparingly soluble salt represents an equilibrium system. Our example was sodium chloride. Well, actually, that's not a sparingly soluble salt. A sparingly soluble salt in our examples today was silver chloride. Plus. Okay, there's a sparingly soluble salt in equilibrium with its ions. So what does that mean? Well, I told you at the very beginning that the rate of this reaction to the right is equal to the rate of the reverse reaction. That's what equilibrium means. That was 3. Now number 4. Phenolphthalein was our indicator for acid-base reaction. So what the question is asking you here is, phenolphthalein itself is a weak acid. In fact, all acid-base indicators are either acids or bases themselves, and they undergo reactions concurrent with the reaction that you're studying, except that it doesn't take much of them to change color. So what is it asking? It says, use the scientific encyclopedia or online reference to find the formula of phenolphthalein. So that's simple. Just what is the molecular formula of phenolphthalein? Look it up. And then what's the IUPAC name? IUPAC. International Union of Pure and Applied Chemists. This is the governing body for naming compounds. So the name for phenolphthalein is going to be that long, and you don't have to know what it means. You just have to find it. So you look for phenolphthalein, and it's written for you in your document, and be sure that it says IUPAC name. And then just copy it. And then the third question is, at what pH does phenolphthalein change color? Well, usually pH of color change is a range, like between this pH and that pH. Right? So by this time, you should know what pH is. Right? And I'll just define pH is the negative log of the hydrogen ion concentrations. That's just another expression for acidity. Right? So if it's less than 7, it's acidic. If it's greater than 7, it's basic. Okay? So what's the pH range for phenolphthalein for its color change? You can find that in the literature too. All right, let me see. Am I going to help you with the rest of them? No, those were our those are pre-lab questions. Okay, post-lab questions. Post-lab. Okay. Question 1. Explain how a saturated solution represents an equilibrium between the solution and any undissolved solute. You can answer that one. I know you can. We've already answered it. Addition of 12 molar HCl to saturated sodium chloride results in precipitation of sodium chloride. We observed that. But the diluted hydrochloric acid added to sodium chloride meant there were no precipitates formed. And the hint I gave you there was a dilution factor. So go back and look at it and explain it. How do you explain why the addition of silver nitrate to the iron thiocyanate equilibrium had an effect on the equilibrium, even though neither silver nor nitrate ion is written as part of the equilibrium reaction. Right? I'll just give it to you in one word: coupled. Coupled reactions. That's 2 words, actually. Number 4, when you add concentrated ammonia to silver chloride equilibrium solution, the silver chloride solid dissolved as the soluble silver ammonia complex formed. I showed you that. When you subsequently added nitric acid, the silver chloride reprecipitated. Explain it. And I did that also on the board. All right, so that's it. That's all the help I'm going to give you. You should be able to figure that one out very nicely. And that's our lab on LeChatelier's principle, stresses applied to an equilibrium system.